To truly appreciate water's weirdness, first we need to understand its blueprint, the phase diagram. Because right here, at the fundamental level of how phases interact, water is already breaking the rules. On the horizontal axis, we have temperature in degrees Celsius. And on the vertical axis, we have pressure, typically shown in pascals or atmospheres. The diagram is then divided into 3 regions, each representing a different phase: solid, liquid, and gas. These curved lines are also known as phase boundaries, lines that represent the conditions where 2 phases can coexist in equilibrium. If we draw a line across these boundaries at the ambient atmospheric pressure, or 1 atmospheric, we will find 2 points that we are all very familiar with: thermal equilibrium at 0 degrees and the boiling point at 100. Tracing down the phase boundary, we can see that the boiling point gets lower as the pressure decreases. Meaning, at high altitudes, you can boil water at lower temperatures and enjoy a freshly brewed tea that won't burn your mouth. Following down the axis, we will eventually reach a point where all 3 phase boundaries meet. This is the triple point, the only set of conditions where ice, liquid water, and vapour can all exist together in perfect balance. Below this point, liquid water is no longer stable and transitions directly between solid and gas. An example of these extreme low pressures can be found on Mars, where water cannot exist as a liquid. Under its thin atmosphere, liquid would boil away almost instantly, and the rapid heat loss would cause the rest to freeze into ice. A similar experiment can be carried out right here on Earth by throwing boiling water into the air on a bitterly cold day. The hot droplets are already carrying a lot of thermal energy, and once dispersed into freezing dry air, that heat is lost almost instantly. Some water molecules escape directly as vapour, while the remainder cools so fast the droplets solidify into ice crystals. So just like on Mars, the water is being pushed across the phase diagram into regions where liquid isn't stable. Moving up the boundary from the triple point, we can see the line between liquid and gas eventually comes to an end, a point beyond which the line simply disappears. This is known as the critical point. Beyond these conditions, water becomes something entirely different, with no distinction between a gas-like and liquid-like state, also known as a supercritical fluid. When this state of water is put to use, engineers refer to it as supercritical steam, which is far denser and more energetic than ordinary steam, capable of carrying heat with remarkable efficiency. It flows like a gas, but transfers energy like a liquid. That's what makes it so valuable for generating electricity in advanced power systems. The behaviour of water along the liquid-gas phase boundary is not unusual. The steadily rising curve with increased pressure up to the critical point is in fact almost a universal feature shared by nearly all liquids. But where water starts to break the rules is here, along the solid-liquid boundary. For most substances, increasing pressure makes the solid phase more stable. Out of more than 200 million known substances on our planet, water is one of only a handful that behave the opposite way. Iron, for example, behaves just as we'd expect. Deep inside Earth's core, where pressures reach millions of atmospheres, iron remains solid even at temperatures over 5,000 degrees Celsius. But farther out at lower pressures, that same iron begins to melt, forming the liquid outer core that drives Earth's magnetic field. In other words, for almost every substance on the planet, squeezing harder raises the melting point, with water being one of the rare exceptions. The fact that the solid-liquid phase boundary slopes towards the left might seem insignificant, but its effects ripple through everything from everyday life to the planet itself. It's one of the reasons a skate blade glides so effortlessly across ice. Although it is not the pressure from the blade alone, ice is coated by a thin liquid-like surface layer, and the moving blade can generate additional meltwater through friction. Together they create the microscopic lubrication that makes skating possible. It also helps explain glacier motion. Deep beneath a glacier, immense pressure can bring the basal ice close to melting, and the water that forms there can help the glacier slide over the ground below. Perhaps the main reason we think of water as ordinary is because it's everywhere. We drink it, swim in it, and watch it fall from the sky. Nearly every liquid we encounter on a daily basis is largely made up of water. And perhaps that's why its strangeness hides in plain sight. Although there are a few substances that share some of its anomalies, water is the only substance on Earth found naturally in all of its three phases, forever cycling between them, quietly shaping our world. And while the phase diagram shows how water behaves, to understand why, we have to look closer, beneath the curves and boundaries, into the invisible network of bonds that make the liquid world possible.